Tape delay, 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 tape delay. What's up, YouTube? Today we are going to talk about how to build a tape delay emulation from scratch. And by that I mean a delay which can modulate the delay time smoothly to give warbly pitch bending effects. And in the analog world, this is no problem because mediums like tape are continuous, so they essentially have infinite resolution, and speeding and slowing down the playback speed is no problem. But in the digital world, it's not so straightforward how we do this, and we need to understand how interpolated delay lines work for this. So let's dive into it. This white circle represents a loop of tape, and the red line is a playhead reading back the audio data stored on the tape. And since this tape is in a loop, as the playhead circles around and around, it just repeats the same audio data back. This is kind of like a delay, but the delay time would be fixed to the length of the loop, and it's not a usable effect. To make this a usable effect, we need to be able to receive incoming audio so that we can play it back at some delayed time. So let's introduce the right head, which does just that. This right head, represented by the blue line, is writing the incoming audio to the tape, and then the red playhead, which is lagging behind, will read back that audio and play it through our speakers at some delayed time. And that delayed time is basically the distance between the right head and the read head, represented by the yellow delay arc in this figure. A tape machine is a real analog system, and so it's going to have imperfections. And the playhead is going to wobble a bit, speeding up and slowing down. This gives tape that delicious warble because of the natural vibrato introduced by speeding up and slowing down the playback of the tape. But in a simple digital delay, we don't have the continuous representation of audio. And so the wobble of the read head will really be stepping through time discretely in units of samples. And instead of that nice, delicious warble, we're left with cold digital artifacts. In order to get smooth modulation with a digital delay, we need to scan the delay time at a resolution that is finer than the digital sample period. And for this, we need an interpolated delay. This introduces a second read head, which is represented here by the orange line, which lags behind by one extra sample. Then what we can do is interpolate between the orange and the red read heads to estimate the waveform at a finer resolution. This can be as simple as essentially drawing a straight line between the samples, which is known as linear interpolation, but we can use more sophisticated interpolation algorithms, which might sound better depending on our application. I am going to use all-pass interpolation, which uses the phase shift of an all-pass filter to add intersample delay. So here's an example of the delay we're going to build. I have soloed the track with the delay on it. And we can turn up the mix to exaggerate it so you can hear what it sounds like. And here's the track with the delay bypassed. And then one more time, we can turn the delay back on and mix it in and play with the warble and delay amounts to show you the kind of pitch shifts that we can get from this plugin. And lastly, let me show you with the context of this little demo track. let's disable this delay plugin, and then let's rebuild it from scratch so you can see how all the details work. Now I'm going to make this big, and the first thing I want to do is delete all of this and rebuild it with the multi-channel plug in and plug out, and that gives us a little bit cleaner setup because there's just one wire for our stereo channel. So if we pass just this one wire through, I can show you this is just feeding our signal into the plugin and back out. The next thing we want to do is add a buffer, and a buffer is just a chunk of memory, so it's just gonna contain our audio data. And I'll leave a little comment here. This is 10 seconds of audio data and memory. And then we can copy this to get the right channel of our memory. Let's make a gen object called interpolated delay. So let's open up this gen object, and let's first define what the inputs and outputs for our delay algorithm are going to be. Let me add a comment to this first input and say that this is going to be our signal. Our second input will be and say this is the delay time in milliseconds. The third input will be our feedback amount. It's going to be some scalar from 0 to 1. And then our last input 4 is going to be the dampening amount. Next, I'm going to build an object inside of this gen patch. It's going to be another gen patch called two tapped delay. And essentially this means that we're going to be able to get two different delays out of this object. Because remember I said in our interpolated delay algorithm, we want two delays that are one sample apart, and then we're going to interpolate between them. So let's open this up. So this first input, let's add some comments to keep things clean and clear. This is going to be our signal. The second input, this is going to be our delay time 1. And our second delay time for this specific algorithm is always going to be one sample later. So it would be possible to do something like this, and this is kind of our second delay time out of this output, and this is our first delay time. But just to keep this object a little more flexible, let's create a third input called delay time 2, and we can kind of configure this to work with our interpolated delay. All right, so like I said in our tape delay, we're essentially going to want to be continuously writing to our virtual tape, right? So how we're going to do that is using the poke function. This means we're going to write. We're going to write to that location in memory that I called delay left. So this is like our 10 seconds of tape. And let's send the signal to the value to write for our poke function. And then how we are going to scroll through this kind of in a loop is we're going to create a counter. And this counter is going to start at position 1, and it will count all the way into this count limit. And so if we set this, we can get the length of our buffer by this first output of buffer delay left is the length in samples. So we're going to reference this in a couple different places. So I'm going to send out this output and create a variable called dimension. Then if we receive that over here, this counter is essentially going to count from 1 to 48,000, but it's variable. So if we change the length of our tape, this will still work. And then, this output of this counter will go to the position we write to. Okay, so this is basically our write head. And we haven't implemented a delay yet, but let's start getting audio out of this plugin so we can verify things are working and just make this a little more interactive so we don't just have to hear me talking the whole time. So I'm going to read from this delay, and we're just going to read from the same index we're writing to. So we're just going to put this right over there and pass this out. So essentially right after we write this sample, we're going to read from it, and it's essentially as if we connected the input to the output. But let's just test that out and make sure it's working. So I'm going to go through all the layers of my my plugin and make sure the signal is passing through here, and then pass my signal through. And let's hear that. And sure enough, it's just passing the audio through, which is good. That's what we want. But it's only coming through the left channel. So for right now, let's create this mc.unpack item, or sorry, actually mc.pack. And this is going to take two individual like mono channels and pack them into one multi-channel signal. And let's just connect our left channel delay into the left and right channel so we can get stereo out. And let's make sure that's working. Great, so we've tested that this right head over here is working because, you know, whatever we're writing to memory, when we essentially connect that same index to our read operation, we're just passing the audio through, which is what we'd want. That makes sense. So if we want to add a delay, now what we're going to want to do, instead of reading out the same index that we're writing to, we're going to want to subtract the delay time from this write index, which will essentially shift our read operation by this number of samples. Now this would give you some negative numbers, so we're also going to need the modulo operator. And if you're not familiar with this, this makes kind of all the numbers fit into a certain range. It kind of like wraps them around. I like to think of it like how a clock works, like when it's 1 o'clock and you subtract 2 hours, you're at 11 o'clock. But instead of 12 hours, what we're going to do is make this second input, what we want is the dimension of our buffer. So we're going to receive this dimension variable I created, and this makes it wrap around within the space of our kind of 10-second tape delay. So if we send this index to the peak instead, now we are shifting out the number of samples we're reading from, which causes a delay. So remember that this is in samples. So what I'm going to need to do out here is convert this milliseconds to samples. So I'm going to first divide by 1000 to convert milliseconds to seconds. And then let's multiply by the sample rate, which gives us the number of samples that we want to delay. And we need integers, right? So I'm going to use this floor operator, which if we look at the help, it's saying this rounds down the value to the next lower integer. So yeah, even though like the milliseconds coming in are continuous, we're going to round down right here, since our delay only, you know, we're writing and reading samples from this digital memory, we need to be an integer. So we're going to do that. And next thing I want to do is go to the very top level and just put some test amount of delay in and make sure we're getting that out of the output. So let's create our first live.dial object and call this delay time. So if I go over to the inspector and rename this to delay in milliseconds, and then since this is in milliseconds, we can make this range. Well, first off, we want to choose a float. We can choose time, milliseconds, cool. And then we can maybe make the initial value like 250 milliseconds. And where's the range? I want the range to go from, let's say we can go down to like a 1 millisecond delay up to a really long delay, like maybe 10 seconds would be pretty long. So that's 10,000 milliseconds. Okay, now I want to test if we are delaying the signal by the desired amount. So what I'm going to do is add a mix object. But what this does is it mixes the first and the second inputs by this amount. So all the way over here, it has the first input. Here has the second input, and this is somewhere in between. And this will just help us be able to hear if we're actually delaying from the dry signal. Great, so the delay is working, but check this out. When we change the delay time, we get all those harsh digital clicks. So this is where we're going to want to add an interpolation feature to our delay. So let's add the interpolation feature. We're going to open up this interpolated delay, and now from our tapped delay, first off, we're going to want to get our second output. So since we set this up this way where we have two inputs for the two different delay times, we can really just copy this whole chain and select this third input instead, this delay time 2, and still connect the counter over there, and we can put this out of output 2. And to test this out, let's see, I guess to test this out, it might be kind of cool to first just shift this by some amount of samples and see if we don't get two delays out of our output. So we can just kind of add them together. Let's just see if this works. Okay, that is definitely adding two delays to our output, but we don't just want to add 1200 samples, we actually want to add just one sample. So we're going to add one here. And now our second delay output is one sample behind. And now what we can do is interpolate between these two delay outputs, which are one sample apart. All right, I've pulled up on the left-hand side the textbook I've been following, so we can use it as a guide to figure out how to do this first order all-pass interpolation. So what we want to first do is figure out how much do we actually want to delay the signal by. So right here was kind of our desired delay time. If we weren't dealing with discrete digital samples, this is how much we would want to delay the signal by. Even though it's in units of samples, this is a continuous number out of this input. And then this input down here rounded it down to the next integer. So this is where we kind of digitized or discretized the incoming delay time. So if we want to get back this delta number in this algorithm, what we do is we're going to subtract the desired time. We're going to subtract off the actual like integer number from it. So to keep things nice and clean, let's create yet another gen object called all-pass interpolation. I'm going to open this up. This first input, I'm going to leave a comment. This is our signal, and our second input is going to be signal, or I have to put quotes, signal delayed by one sample. And then our third input is going to be our interpolation amount. So you might be wondering, since this second input to our interpolation algorithm is just this signal delayed by one sample, why did we need a tapped delay output? Why couldn't we just have a regular delay with this one, and then essentially inside of this interpolation algorithm use a delay with one sample, which is the same thing in gen. This history is also a one sample delay. So why is this different than this? Okay, this animation shows what we want. This is where the orange and red read heads are one sample apart, and we can interpolate between them to get a continuous delay time. But this animation shows over here what happens if you do that kind of naively with two sequential delays, and that gives you an effed up delay, because as you can see in this animation, it's true that the orange read head is lagging behind one sample of the red delay, like in a sequential manner. Like it's like following the actual red read head, and the orange read head is kind of, it's flipping between being in front of the red delay and behind it. And that's just because of the way we're actually modulating the delay time. So it's true that the orange read head is one sample behind the red one, but like with respect to the blue read head, it's kind of going forward and back in time, and it becomes really hard to actually interpolate. Like you don't really know whether you're in which direction you're interpolating in, and it's all effed up. It sounds really bad. What you actually want is this one. So this is why I created the tapped delay head to give two outputs, and with respect to the blue right head, we're always one sample apart in the same direction. So let's go ahead and implement it over here. First off, we want to convert this delta amount into the eta that's actually used in the formula. So what we're going to do is the exclamation mark minus 1, which does 1 minus the input. So this is going to give us 1 minus the interpolation amount. And then we are going to get plus the input like that. And then we're going to divide these two signals. And then I'm going to create a variable called eta. And in the formula, I actually have to scroll down a little bit. That's over here where they're converting this desired shift, that delta, they're converting it to a variable called eta. And then that's what's referenced in this main formula. So then we can go over to this formula and we're going to first subtract x of n, which is our incoming signal, from y of n minus 1, which is our output delayed by one sample. We don't have our output yet, so I'm just going to leave this input empty for now. We'll just connect that. And then we're going to multiply all of that by this eta variable. And then what we're going to do is we're going to add our previous input. We're going to add x of n minus 1. Now this is actually the whole formula, except we haven't completed it. We haven't kind of added that y of n minus 1, but this signal right here is our output. And then in our feedback loop, we're going to add this history function first. That's a single sample delay you can see in the comment. So we're going to add this here, and then this can feed back. This is now our y of n minus 1. And so I'm going to close this out. We're going to add some features here in a second, but we want to test all pass interpolation first. So let's close this out. And then I'm just going to paste in these blocks from my original patch just for the sake of time. It's really just adding an LFO that goes from 0 to 10 hertz. And we can just reconnect this. Let's first test out how this modulated delay sounds. So you can hear the warble is definitely kind of speeding up and slowing down the playback speed of this delay line. Now let's test out the interpolation by turning the mix all the way up so we can just focus on listening to the modulated delay. And let's bypass this all pass interpolation and hear what that sounds like. Yeah, I can definitely hear how with this all pass interpolation disabled, we get a lot of crunchy artifacts. So let me reconnect this and then we can do some quick A/B tests. Yeah, so you can definitely hear how this all pass interpolation is smoothing out a lot of the artifacts. It's definitely doing its job. Another interesting thing about this is we have no feedback in the delay yet. We have the mix all the way up. All we're really doing is changing the pitch of this incoming signal. So we've kind of also inadvertently created a tape vibrato type of emulation with this setup or this configuration. All right, so the main point of this video was getting this interpolated delay working, but just to make this effect a little more complete, I've added a couple more features and I'll just walk through them quickly. So the first thing is adding some saturation to kind of simulate as you're writing to tape. There's a little bit of saturation, and this tan-H is a very basic approximation of tape saturation. We could do a video in the future on hysteresis, which is how you'd get more accurate tape saturation out of a plugin. So let me know in the comments if that's something you'd be interested in. After the tan-H saturation, we have a one-pole low-pass filter. It's a really simple algorithm that looks like this. And this control will just open and close the low-pass filter. And this is in the feedback loop. So the output of our delay gets low-passed, but also each time the feedback loop goes through, we'll kind of dampen the signal more and more. And then this history, as I've mentioned previously, this is just a single sample delay. And we actually need this just to make the feedback loop work. If I were to just try and take this output and feed it back in fact, this program won't even let you do that because it's just kind of, it doesn't work. You need some sort of delay and a feedback loop. And since we've added this one extra sample of delay right here, what I've done is I've subtracted one sample of delay from our kind of parameter coming in, just to make sure this is a sample accurate delay. And then over here, we're just going to control the amount of feedback by essentially attenuating the signal each time it goes through this loop. This DC block, this DC block is just a high pass filter that will just get rid of some DC frequencies, because in a feedback loop that can get pretty nasty. So that's pretty much all we've added in this main delay algorithm. I've also turned this into a stereo delay by basically copying and pasting this and just sending the left and right channels to the respective delay. And then on the top level of our patch, I've just added some controls for feedback and dampening. And I have also added the some averaging for when we move this dial. And the reason we need that is just the resolution of this dial is really poor. So like it kind of defeats the purpose of having an interpolated delay if you're asking it to interpolate jumping around by like several milliseconds. That'll just always sound choppy. So this just kind of gives us a smooth output outside of our dial. Cool, so now we have a feature complete delay. So yeah, I'll give a link to download this interpolated delay plugin in the description. Definitely download it, play around with it. Let me know if you have any suggestions. Kind of the whole point of learning to do things from scratch is so that then you know where to improve on or add some interesting twists or features. So yeah, I guess I will close out this video by playing around with it a little bit myself. Since we've been playing around so much already on this pluck sound, maybe I can put another instance on like this whole bus with like all the synths going into it and seeing what that sounds like. Wobbly and warm. Definitely probably too much of that effect, but just wanted to demonstrate it. Anyway, hope you enjoyed watching, and I'll see you next time.